In the name of Almighty God, I am Mahsa Sankasha, and today I want to talk about Introduction to Electrodeposition module in COMSOL multiphysics simulation software. Now I want to go through meshing device. The default triangular two dimensions or tetrahedral three dimensions mesh is normally suitable for solving the equations describing conservation of charge and mass for a general electrochemical problem. Electrochemical models involving mass transports generally benefit from a finer mesh at the electrode surfaces and at a singularity such as the boundary between an electrode surface and an isolating surface. This may be accomplished by adding additional size mesh nodes for these boundaries only, also considering refining the element growth rate and/or using boundary layer meshing in three dimensions. Sometimes a regular map mesh can be more appreciated in a rectangular two dimensions domain. Such domains are common in Cutway schematic studies of batteries and fuel cells. Similarly, the SIP mesh is often appropriate for very thin layers in a three dimensions model. For fluid domains, the default physics-controlled mesh should be used, with boundary layers as required. For some problem with a stationary fluid velocity field and time-dependent convection of electrochemically reacting species, it may improve convergence to set up a refined mesh without boundary layers for the species transport study step. Now I want to go through meshing in the COMSOL Multiphysics Reference Manual, solving electrochemical models. Due to the highly nonlinear nature of electrode kinetics, some electrochemical models can be difficult to solve. This section includes some general tips and tricks to facilitate model solving, troubleshooting, and to improve solution accuracy. The general current distribution problems starts with the following suggestions if you encounter difficulty solving a problem. Make sure that the potential levels are bootstrapped somewhere in the model, preferably by grounding one electrode. If there is no potential level defined anywhere in the model, your model may have infinitely many solutions and the model will not converge. Consider using a stationary with initialization or a time-dependent with initialization study. Both these studies will use a current distribution initialization study step as a first step to solve for the potentials only. If you run into problem solving for the second step in this study, you may have to change the current distribution type setting to secondary on the current distribution initialization study step node and also review the initial values as described in the next bullet. Review the initial values, especially the potential. Suitable initial potential values can usually be derived making a potential walk through the geometry starting at the grounded boundary. Compute electrolyte and electrolyte potentials in other domains by assuming equilibrium potential differences between electrode and electrolyte for the main electrode reactions. Switch to linearized Boosler-Volmer kinetics or primary current distribution while troubleshooting. This can be useful to help achieve a solution for a model that doesn't solve with nonlinear kinetics, thereby indicating suitable initial values for the nonlinear problem. If your model contains porous electrodes, try refining the mesh resolution in these domains, especially toward the electrolyte boundaries. Now I want to go through the electrochemistry interfaces, specifying initial values and inspecting and troubleshooting measures in the COMSOL Multiphysics Reference Manual. Electrochemistry coupled to mass transport. If the model involves electrochemistry coupled to mass transport, here are a few things to try to help improve model convergence. Review the initial values for the concentration values. Zero initial concentration values can be unsuitable for tertiary current distribution problems and battery simulations, since they could imply that no charge carriers or no reacting materials is present. If steep concentration gradients are expected close to electrode surfaces, use boundary layer meshing or finer mesh size settings at these boundaries. When setting up user-defined kinetic expressions, avoid evaluating negative concentrations by using expressions such as max C and epsilon to the power of 2, where epsilon is the machine epsilon, a very small but finite number. Try to solve for low currents and low overpotential first, then increase the cell load for stationary problems. This can be done using an auxiliary sweep with continuation. If a problem involving mass transport is hard to solve for high currents but solves for low currents, it might be due to mass transport limitations. In this case, review the transfer parameters values and check that the current magnitudes are reasonable. If the current densities are unreasonably high, review the electrode reaction settings. For time-dependent problems that run into convergence problems after a certain time, review the solution at the last time step. If the solution of a reactant reaches zero or a maximum value for insertion electrodes in the batteries, when the convergence issues occur. The current load of the model is too high in real relation to your initial concentrations or mass transfer properties. Now I want to go through the electrochemistry interfaces. In the COMSOL multiphysics reference manual, two dimensions and three dimensions boundary layer meshes, a stationary and parametric sweep. Setting up a study sequence for a multiphysics problem. For multiphysics problems, try to adjust the study sequence, solve certain physics interfaces in the sequence. This can, in many cases, reduce computational time and improve convergence. Analyzing the results when solving the physics interface separately can also help when troubleshooting a non-converging model. A good strategy is often to solve for the potentials only, that is, disable mass transport and flow interfaces. Using a stationary study set before solving the full model in the study sequence. In this way, the stationary solution is used as initial values for the following steps. This can be manually by modifying the settings of the study node or in an automated way by using the stationary with initialization or time dependent with initialization study sequences as described above. In many models, the flow profile is only slightly or not at all affected by changes in current density. Therefore, it can be a good strategy to solve separately for the flow early in the study sequence and then solve for the other physics interfaces in the subsequent steps. If the flow is not affected at all by the current distribution, solving for the flow can be disabled entirely in consecutive steps. Now I want to go through electrochemistry interfaces in the COMSOL Multiphysics Reference Manual, studies and solvers, analyzing model convergence and accuracy, achieving convergence when solving nonlinear equations. Time-dependent problems with low steps. For time-dependent problems, try the following to address accuracy and convergence issues with regards to sudden current or potential load steps. Use smooth current or potential load functions in order to avoid instantaneous or discrete loud steps. Add a double layer capacitance to the model, which can improve the numerical stability, reduce the maximum step taken by the solver if you want to prevent the solver from using short square load steps, or change the steps taken by solver setting from free to strict or intermediate. To control the time steps using the times text field using the events interface can also be an option in certain cases if the load cycle itself varies dynamically. Now I want to go through double Layer capacitance in the COMSOL multiphysics reference manual is step and time dependent. Building a COMSOL multiphysics model and the events interface. Solver settings. Try adjusting the solver settings. In rare cases, try to increase the maximum number of iterations. If you know the order of magnitude of the dependent variables beforehand, setting the scaling method to manual for these can improve convergence and the accuracy of the results. This may be of special importance when solving for concentrations that are initially very small but where the final order of magnitude is now appear. This could be the case for the active species in a battery model, for example. In the COMSOL Multiphysics Reference Manual, I want to go to studies and solvers, analyzing model convergence and accuracy, achieving convergence when solving nonlinear equations, and electrochemistry studies and study steps and cyclic voltammetry in the COMSOL Multiphysics Reference Manual. In the multi-component systems, it is rarely straightforward to predict the rest potential and direction of current flow. The current initialization step in COMSOL multiphysics does this for you, but it's only correct if concentrations and formal potentials for all electrode reactions are specified precisely and with respect to a common reference scale. Now I'm gonna go through electrochemistry studies and study steps into COMSOL multiphysics reference manual, studies and solvers, and building a COMSOL multiphysics model in the COMSOL multiphysics reference manual. Now when I go through post-processing your solution, potential variables, several different potential variables are available for post-processing and during computation. The most common ones are described in table 2-1, and you see that we have a variable field and the description is electrode phase potential defined at electrolyte and porous electrode domain. The next variable is phase electrode phase potential define an electrode and porous electrode domains. The next variable is x66.physics. Description is electrode phase potential, define an electrode reaction boundaries to electrolyte domains. The next variable is equation underline y. Description is equilibrium potential and define an electrode reaction boundaries and porous electrode reaction domains. The next variable is x66.eta underline y and description is overpotential and defined at electrode reaction boundaries. Current variables and calculating the total cell current. The current density may vary between locations on an electrode surface. This effect is very important to understand through modeling because it cannot be directly measured. Experimental measurement can only return the total current drawn at an electrode, although the variation in current density can be inferred by other means. To calculate the total current in quantum multiphysics, it is necessary to integrate the total drawn current density along the boundary or over the domain of the electrode. Some common current density variables are shown in table 2-2. We have a variable NLL and the unit is ampere based on square meter. The description is electrolyte current density in normal direction and defined at boundaries to electrolyte and porous electrode domains. The next one is NLS. The unit is ampere per square meter and the description is electrode current density in normal direction, defined at boundaries to electrolyte and porous electrode domains. And you see the next table is common current density variable. I just read the description. We have a local current density of electrode reaction based on ampere per square meter, defined at the electrode reaction boundaries, total interface current density, local sum of all x location underline y defined as electrode reaction boundaries. The next one is volumetric current density of a porous electrode reaction and defined as porous electrode domains. It's based on ampere per cubic meter. The next variable is total volumetric Current densities, local sum of all IBM Rely irradiate, the defined at porous electrode domains based on ampere per cubic meter electrode current density magnitude, f to the power of 2 norm, and defined at electrolyte domains. The unit is ampere per square meter. The next description is electrode current density magnitude, f to the power of 2 norm, and defined at electrode domains. The unit is ampere per square meter. If in one dimension or one dimension axisymmetric, the electrode is implicitly uniform, so you can just multiply by the area of the electrode. In two dimensions and or two dimension axisymmetric, compute the appropriate line integral. In three dimensions, compute the surface integral. You can also define your own total current variable by using an integration non-local coupling across the electroactive boundaries. This variable can also be used during the computation in one-dimensional axisymmetric and two-dimensional axisymmetric components. Make sure to select the compute integral in revolved geometry checkbox. In the COMSOL Multiphysics Reference Manual, non-local couplings and coupling operators and integration. Avoid evaluating the some variables on boundaries, for example, is mag and mag. These are generally less accurate than the NLL and NLS variable. Now I want to go to electrochemistry interfaces. This chapter describes the physics interfaces and features to model electrochemical cells. The physics interfaces described are found under the electrochemistry branch. In this chapter, we want to go through the various subsection for electrochemistry branch. The first one is the primary and secondary current distribution interfaces. Next is the tertiary current distribution nearest plug interface. The next one is the current distribution boundary element interface. The next one is shared physics features in the current distribution interfaces. The next one is the aqueous electrolyte transport interface. The next one is the concentrated electrolyte transport interface. The next one is the electrode shell interface. The next one is electroanalysis model wizard tree and theory for the current distribution interfaces, theory for the concentrated electrolyte transport interfaces, theory for the electrochemical heat sources, theory for electrochemical power losers, theory for the electrode shell interface, theory for electroanalysis, and electrode potentials and reference electrodes. The primary and secondary current distribution interfaces. In this section, we want to go through the primary current distribution and second current distribution interfaces and also other sub-branches such as electrolyte initial values, porous electrode, periodic condition, thin electrode delete layer, edge electrode, electrode line current source, electrolyte line current source, electrode symmetry axis current source, electrolyte symmetry axis current source, electrode point current source, electrolyte point current source. Only the physics interface specific nodes are described here. All other nodes in the primary current distribution and secondary current distribution interfaces are described in shared physics features in the current distribution interfaces. The primary current distribution and secondary current distribution interfaces, the primary current distribution interface and the secondary current distribution interface are found under the electrochemistry branch when adding a physics interface. Primary current distribution interface. The primary current distribution interface defines the transport of the charged ions in an electrolyte of uniform composition as well as current conduction in electrodes using Ohm's law in combination with a charged balance. The physics interface neglects activation over potentials due to charge transfer reaction. Use this physics interface to estimate the ohmic losses in simplified models of electrochemical cells, where the overpotentials of the electrode reactions are small compared to the ohmic voltage drops in the electrolyte and electrodes. Now I'm going to go through secondary current distribution interface. The secondary current distribution interface is similar to the primary current distribution interface except that it is also accounts for activation over potentials. The relation between charge transfer and over potential can be described using arbitrary kinetic expressions such as Butler-Warmer and Toffel equations. Use this physics interface for generic modeling of electrochemical cells. It can be combined with interfaces modeling mass transport to describe concentration-dependent tertiary current distribution. Use the current distribution type settings on the physics interface node to describe below to switch between a primary current distribution and a secondary current distribution instance and interface. Now I'm going to go through Introduction to Electrochemistry Modeling. The first section is settings. The label is the default physics interface name. The name is used primarily as a scope prefix for variables defined by the physics interface. Refer to such physics interface variables in expressions using the pattern name and then variable name in order to distinguish between variables belonging to different physics interfaces. The name string must be unique. Only letters, numbers, and underscores are permitted in the name field. The first character must be a letter. The default name for the first physics interface in the model is CD. Now I want to go through domain selection. Domains that don't conduct current should be omitted from the domain selection. For example, the gas channels in a fuel cell. Now I want to go to the out-of-plane thickness for two dimensions component, integral value or expression for the out-of-plane thickness d. The SI unit is meter. The value of d determines the size of the domain perpendicular to the model two dimensions cross-section. This value yields, for example, the correct total current when the current density is obtained from a two-dimension simulation. Now I want to go to the cross-sectional area for the one-dimensional components. Inter a cross-sectional area AC SI unit is based on the square meter to define a parameter for the area of the geometry perpendicular to the one-dimensional component. The value of this parameter is used, among other things, to automatically calculate the total current from the current density vector. The analogy is valid for the other fluxes. The default is 1 per square meter. Current distribution type. The current distribution type selected in the list is based on the choice made when adding a physics interface, primary or secondary. The primary current distribution interface changed a secondary current distribution interface if the choice is changed to secondary and vice versa. The selection between primary or secondary governs how electrode reactions are modeled on the interfaces between electrodes and electrolytes. Models using a primary current distribution type use potential constraints, Dirichlet boundary conditions according to the equilibrium potential settings. Secondary current distribution models use current flux conditions and Newman boundary conditions according to the sum of electrode reaction current densities. Now I want to go through physics versus materials preference electrode potential. The physics versus material reference electrode potential setting on the physics interface node can be used to combine material library data for coil densities and equilibrium potentials with an arbitrary reference electrode scale in the physics. The setting affects the electrode potentials used for modeling put into the materials node as well as all equilibrium potential values output from the materials node. Note that the settings will only impact how potentials are interpreted in communication between the physics and the materials node. If the from material option is not in use for equilibrium potentials or electrokinetics, the settings has no impact. Now I will go through the dependent variables. This physics interface defines dependent variable fields for the electrolyte potential and electric potential. The names can be changed, but the name of fields and dependent variables must be unique within a model. Now I'm gonna go through the discretization. The interface uses linear elements by default, and this setting is recommended for most problems. Certain types of problems, such as models using porous electrodes or current contribution problems in two dimensions or higher, may benefit in terms of solution accuracy from using quadratic elements. In multiphysics models, it is generally recommended to use the same elements ordered in all cubed interfaces. To see all settings in this section, click the Show More option button and select Advanced Physics option in the Show More option dialog. Now I want to go through the electrochemical reactions and difference between a primary and a secondary current distribution. Domain equations for primary and secondary current distributions. The next one is shared physics features in the current distribution interfaces. The next one is theory for the current distribution interfaces. The next chapter is secondary current distribution, rotating cylinder rule cell application library path is electrodeposition module verification example, and the name is rotating cylinder rule cell. Now I want to go through the first properties is electrolyte. Use the electrolyte node to define an electrolyte domain that only conducts current in the ion conducting phase. Note that electrolyte in this case doesn't refer to the pore electrolyte in porous electrodes, which should be defined by a porous electrode node instead. The electrolyte conductivity sigma L in the SI unit is based on S parameter. Parameter will define how the current in the domain depends on the gradient of the potential. Now I'm going to go through domain equations for primary and secondary current distributions and electrolyte theory. The first chapter is initial values. Use this node to specify the initial values of the electrolyte potential and electric potential for the solver. For many electrochemical problems that use nonlinear electrode kinetics, such as Butler-Volmer kinetics, providing reasonable initial values can significantly improve solver convergence. A good value for the electric potential SI unit is based on work in electrode and porous electrode domains can usually be derived from the boundary conditions. For instance, if a boundary has been grounded or set to cell potential, use that value as the initial values also in the adjacent domain. For the electrolytic potential based on SI unit is based on work. A good initial value is often the negative of the equilibrium potential of the grounded electrode. Note for the primary current distribution or for models solved using current distribution initialization study, step search to primary. The settings of this section usually have limited impact on the solver convergence. Porous electrode. The porous electrode node sets up charge balances for the electrode and the pore electrolyte in a porous electrode. Note that the node should be used for porous domains that conduct current in both an electrolyte and an electrode phase. For the case of domains that don't certain a pore electrolyte, for instance, a current collector, feeder, or a gas diffusion layer (GDL) in a fuel cell, use a current conductor node instead. Use porous electrode reaction subnodes to define the charge transfer reactions that occur on the interface between the electrolyte and electrode phases within the porous electrode. For the secondary current distribution interfaces, the porous matrix double layer capacitance subnode is also available. The conductivities are taken from material by default from the respective material list. You can use any material in the model. If present by default, they are set to domain material, which is the material applied to the active domain in the material node. You can use the effective conductivity correction factors to account for the lowered effective conductivities of the electrode and electrolyte phases due to the lower volume fractions of each phase and the tortuosity of the porous matrix. The electrode volume fraction is used to calculate the effective electric conductivity of the porous matrix when the correction factor is set to Brugman or tortuosity. Additionally, it is used in calculating the active specific surface area of the porous matrix when particle-based area option is selected in the child node. Now I'm gonna go to the dissolving deposition species. Use the settings of this section to define species that participate in dissolution deposition electrode reactions within the porous electrode, for instance, metal deposition dissolution or oxide formation. Use the add and delete buttons are needed in the tables to control the number of species. Dependent variables for the volumetric molar concentrations are added for each dissolving depositing species. These variables can be used to keep track of the amount of reacted material in the porous electrode. The total molar dissolution deposition rate depends on the reaction rates and stoichiometry defined in the porous electrode reaction subnode. The density and molar mass determine the electrode growth velocity and the resulting dissolved deposited layer thickness by multiplying by the electrode surface area. In the case of multiple electrode reaction, the average surface area is used. The change in electrode and electrolyte volume fractions can be also calculated by use of the add volume change to electrode volume fraction not available for separator node of tertiary current distribution interface and subtract volume change from electrode volume fraction checkboxes. You can define how these volume changes should be included in the model. Thickness variables based on the surface area are also defined that you, for instance, can use to couple to the film resistance C below. Now I'm gonna go to the absorbing, desorbing species. See the electrode surface node. Film resistance. See the electrode surface node. Domain equations for primary and secondary current distribution. Porous electrode theory. Periodic condition. Use the periodic condition to define a periodic relation between two boundaries, for instance, in a model describing a repetitive unit cell. Use the apply for electrolyte phase and apply for electrode phase checkboxes to enable the periodic condition for the electrolyte and electrode phase potential respectively. By specifying a potential difference, and offsetting potential typically per unit cell can be described. For more information, see periodic boundary conditions in the COMSOL Model Physics Reference Manual. I want to go through the thin electrolyte layer. The thin electrolyte layer node can be used to model a thin insulating or resistive sheet located on an interior boundary in an electrolyte domain. The node can be used as an alternative to drawing the actual layer domain in the model geometry, which may significantly reduce meshing and solver time, especially in two-dimensional models. Thin insulating sheets are commonly inserted in the electrolyte in various types of electrochemical cells. For example, they may be used for optimizing the current distribution in a corrosion protection application or for optimizing the local deposition rate in a deposition bath. The layer may be set to be either insulating or resistive. For the case of resistive, the surface resistance can either be set directly or calculated from thickness and conductivity values. Now I want to go to advanced settings. Enable a slit electric potential in porous electrodes to make the layer fully insulated for the electrode phase potential along the selected boundaries. Now I want to go to the edge electrode. The edge electrode can be used in two-dimensional problems to define electrodes such as long pipes and thin wires where the electric potential variation between the electrode in the normal direction to the electrode surface is negligible. This assumption allows for the thin electrode domain to be replaced by a lumped one-dimensional partial differential equation formulation on the edge. describing an electrode surface along the edge with a given edge electrode radius. In this way, the problem size can be reduced and potential problems with mesh anisotropy in the thin layer can be avoided. The electric current conduction in the tangential direction of an edge can be described by Ohm's law or a fixed electric potential or a floating potential assuming infinite conductivity of the edge or an external short electric potential which allows to connect two electrodes or an external connector with a given bulk resistance or a connection point electric potential which allows to define a location for connections to other locations in the model. An edge electrode can only be applied to edge within or adjacent to electrolyte domains. A defined electrode reaction subnode is added by default to the feature double layer capacitance, external current source, electric ground, electric potential, and electrode current subnodes can also be added to the feature. Now I want to go through the dissolving depositing species. Use setting of this section to define species that participate in dissolution deposition electrode reactions on the edge electrode, for instance, metal deposition, dissolution, or oxide formation. Use the add and delete buttons as needed in the tables to control the number of species. Dependent variables for the molar concentrations SI unit, which is based on mole per meter, are added for each dissolving depositing species. These variables can be used to keep track of the amount of reacted material on the electrode. The total molar dissolution deposition rates depends on the reaction rates and stoichiometry defined in the electrode reaction subnodes. The density and molar mass determine the electrode growth velocity and the resulting dissolved deposited layer thickness, so that the change in the edge electrode radius also can be calculated by use of the add volume change to edge radius checkbox. You can define if this volume change should be included in the model. A thickness variable is also defined. Use it for instance to cope to the film resistance. See below. Decorating plating application library path, electrode deposition module tutorial, decorative plating. Film resistance. See the electrode surface node. This section is only available when the secondary current distribution has been selected on the parent node. Now I wanna go to the concentrate settings. To display this section, click the Show More Options button and select Advanced Physics options in the Show More Options dialog. The mesh size in the perpendicular direction to the edge should preferably be in the same order of magnitude as the edge electrode diameter in order to achieve good numerical accuracy. Now I wanna go to the electrode line current source. For three dimensions components, use the electrode line current source on edge. For two dimensions component, use it on points. For two dimensions axisymmetric components, it can only be selected on points outside the symmetry axis. Now I want to go through the electrode current source. Enter the electrode current source. QLS SI unit is based on ampere per meter. The default is 0 ampere per meter. Now I'm gonna go through the electrolyte line current source for two-dimensional components. Use the electrolyte line current source on edges. For two-dimensional components, use it on points. For two-dimensional axisymmetric components, it can only be selected on points outside the symmetry axis. Electrolyte current source. Enter the electrolyte current source QLL SI unit, which is based on ampere per meter. The default value is 0 ampere per meter. Electrode symmetry axis current source for two-dimensional axis symmetry components. Apply an electrode symmetry axis current source along the symmetry axis boundary. Electrode current source. Enter the electrode current source QLS. SI unit is based on ampere per meter and the default value is 0 ampere per meter. Electrolyte symmetry axis current source for two dimensions as axisymmetric components. Apply electrolyte symmetry axis current source along the symmetry axis boundary. Now when I go to the electrolyte current source, enter the electrolyte current source QLL based on the SI unit ampere per meter. The default is 0 ampere per meter. External current source, internal and external current source QLS SI unit ampere per meter at the edge electrode. The default is 0 ampere per meter. The next chapter is electrode point current source for two dimensions components. Use the electrode point current source on edge. For two dimensions axisymmetric components, it can only be selected on points located on the symmetry axis. Electrode current source, enter the electrode current source QPS SI unit based on ampere, and the default value number is 0 ampere. Now I'm going to go through the electrolyte point current source for three dimensions component. Use the electrolyte point current source on edge. For two dimensions axisymmetric components, it can only be selected on points located on the symmetry axis. Electrolyte current source, enter the electrolyte current source QPL SI unit based on ampere. The default number is 0 ampere. Electrode current, use this node to define a current source in a point of an edge electrode node. This node is available as a subnode to the edge electrode node when Ohm's law has been selected as the electric potential model. The tertiary current distribution Nernst-Planck interface. Now I'm going to go through the sections. The first one is the tertiary current distribution Nernst-Planck interface, electrolyte, pulse electrode separator reactions, initial values, ion exchange membrane boundary, and thin electrolyte layer. Various nodes are also available and described for the transport of diluted species interface domain boundary and pair nodes for the transport of diluted species interface. All other nodes in the tertiary current distribution Nernst-Planck interface are described in shape physics features in the current distribution interfaces. The tertiary current distribution Nernst-Planck interface, the tertiary current distribution Nernst-Planck interface found under the electrochemistry boundary when adding a physics interface describe the current and potential distribution in an electrochemical cell taking into account the individual transport of charged species ions and uncharged species in the electrolyte due to diffusion, migration, and convection using the Nernst-Planck equations. The physics interface supports different descriptions of the coupled charge and mass transport in the electrolyte. See electrolyte charge conservation below. The electrode kinetics for the charge transfer reactions can be described by using arbitrary expressions or by using the predefined Butler, Wormel, and Toffel expressions. Ohm's law is used in combination with a charge balance to describe the flow of the currents in the electrodes. The charge transfer reactions can be defined as boundary conditions or as source or sinks within a domain in order for the case of porous electrodes. The settings chapter. I want to go through the introduction to electrochemistry modeling. The settings chapter. The label is the physics interface node name that will be shown in the model below 3. The name is used primarily as a scope prefix for variables defined by the physics interface. Refer to such physics interface variables in expression using the pattern that is name then dot variable name in order to distinguish between variables belonging to different physics interfaces. The names string must be unique; only letters, numbers, and underscores are permitted in the name field. The first character must be a letter. The default name for the first physics interface in a model is TCD. Now I want to go to the domain selection. The domains that don't conduct current should be omitted from the selection list. For example, the gas channels in a fuel cell. Out of plane thickness for two dimensions components, the thickness field default value is 1 meter defined as a parameter for the thickness of the geometry perpendicular to the two-dimensional cross-section. The value of this parameter is used, among other things, to automatically calculate the total current from the current density vector. The analogy is valid for other fluxes. Now I want to go through the cross-sectional areas. For one-dimension components, enter a cross-sectional area AC. SI unit is per square meter to define parameter for the area of the geometry perpendicular to the one-dimension component. The value of this parameter is used, among other things, to automatically calculate the total current from the current density vector. The analogy is valid for other fluxes. The default is 1 square meter. Now I want to go through the electrolyte charge conservation. The physics interface features five different descriptions of the cube charge and mass transport in the electrolyte. Use the electroneutrality or the water-based with electroneutrality charge conservation option to model cells with significant concentration gradients of the current carrying species ions. The electroneutrality condition implicitly assumes that all major current carrying ions are included in the model. In addition to the electroneutrality condition, the water-based with electroneutrality option also adds the water auto-ionization equilibrium condition, including proton and hydroxide transport when defining the electrolyte equations. Note that this option adds the concentration variables for porous TCD.ch and hydroxide TCD.OH automatically, and that dependent variables for these two species should not be added under dependent variables underneath. With the setting to control the initial pH in the simulation, set the initial concentrations of the other ions in the simulation such that the matching concentrations of proton and hydroxide ions match the pH desired. For pH below 7, add and set the concentration of anions. For pH above 7, add and set the concentration of cations. For example, for a water-based system which only color minus an initial concentration for color minus of 10 to the power of minus 5 m will result in an initial pH of 5. This is analogous to acidifying the solution using HCl. A supporting electrolyte describes a situation where the major part of the charge is transferred by ions whose concentration can be described as constant. Use the electroanalysis no potential gradients option to model electroanalytical problems with electrolyte solutions containing a large quantity of inert supporting electrolyte with a conductivity too high that ohmic losses can be assumed to be negligible. The electroanalysis option will not solve for the electrolyte potential as a dependent variable, setting it to a constant value of zero. Migration effects are hence neglected. Domain and boundary nodes only applicable to the electrolyte phase potential will be disabled when using electroanalysis. The Poisson option copes the Nernst-Planck equations for mass transport to the Poisson equation for describing the potential distribution in the electrolyte without any assumption of electron neutrality. This option is typically used when modeling problems when charge separation effects are of interest, typically within nanometers from an electrode surface. For the electron neutrality option, from the electron neutrality list sets the species that is calculated from the corresponding condition. Note that it shows all species to be taken from electron neutrality effects the specific boundary conditions that can be set on the eliminated species. For example, flux and concentration settings cannot be set for the eliminated species. The initial values cannot be provided. The choice can also have an impact on the numerics of the problems. Physics versus materials preference electrode potential. The physics versus materials reference electrode potential settings on the physics interface node can be used to combine material library data for the current densities and equilibrium potentials with an arbitrary reference electrode scale. The physics. The setting affects the electrode potential used for model input into the materials node as well as all equilibrium potential values output from the materials node. Note that the settings will only impact how potentials are interpreted in communication between the physics and the materials node. If the from material option is not in use for equilibrium potentials or electrode kinetics, the settings has no impact. Advanced settings. To display this section, click the Show button and select Advanced Physics options. Normally, these settings don't need to be changed. Select a material balance. Form a non-conservative, the default or conservative. The selection affects the formulation of the convective term and for porous domain nodes, also the accumulation terms in the non-material balance. For compressible electrolytes, the conservative form should be used. In the absence of convection and electrolyte volume fraction change porosity, the choice between the conservative and non-conservative form is arbitrary. The non-conservative form is usually preferred due to a slighter low computational load. Now I want to go to the dependent variables. The physics interface defines these dependent variables, fields, the concentration of the species, the electrolyte potential, and the electric potential. The names can be changed, but the names of the fields and dependent variables must be unique within a model. Discretization. Concentrations basis function orders higher than quadratic are not recommended if transport by convection is dominating in the model. To see all settings in this section, click the Show More Options button and select Advanced Physics option from the Show More option dialog. Now I want to go to the consistent stabilization and inconsistent stabilization. To display these sections, click the Show More option button and select Stabilization from the Show More options dialog. There are two consistent stabilization methods available and selected by default: streamline diffusion and crosswind diffusion. There is one inconsistent stabilization method, isotropic diffusion, which is not selected by default. Any settings unique to this physics interface are listed below. When the cross-wind diffusion checkbox is selected, a weak term that reduces spurious oscillations is added to the transport equation. The resulting system is nonlinear. There are two options from cross-wind diffusion type: do Carmo and Galileo. The default option, this type of cross-wind diffusion reduces undershoot and overshoot to a minimum but can in rare cases give equation systems that are difficult to fully converge. Codina. This option is less diffusive compared to the DeCarmo and Galileo option, but can result in more undershoot and overshoot. It is also less effective for anisotropic measures. The Codina option activates a text field for the lower gradient limits based on the SI unit is molar per quadratic meter. It defaults to 0.1 mole per cubic meter divided by TDS Helm, where TDS Helm is the local element size. For both consistent stabilization methods, select the equation residual. Approximate residual is the default setting and it means the derivatives of diffusion tensor components are neglected. This setting is usually accurate enough and is faster to compute. If required, select full residual instead. In the COMSOL Multiphysics Reference Manual, see Table 2-4 for links to common sections and Table 2-5 to common feature nodes. You can also search for information, press F1 to open the Help window or Control plus F1 to open the documentation window. Now I want to go through the Nernst-Planck equations, domain equations for tertiary current distribution. using the Nernst-Planck equations and electron neutrality, shared physics features in the current distribution interfaces, theory for the current distribution interfaces. I want to go through the electrolyte chapter. Use the electrolyte node to define an electrolyte domain that only conducts current in the ion conducting phase. The combined charge and mass transfer in the electrolyte is defined by the node. What settings are available in this node depends on the electrolyte charge conservation setting available on the top node. The electrolyte conductivity, which based on the SI unit is S per meter setting, is only available for the supporting electrolyte option. Diffusivity and mobility settings for H plus and OH negative are only available for the electron neutrality water-based option. The convection section is available when the convection checkbox is selected on the interface top node. The velocity field USI unit meter per second of the solvent is specified as a feature input. Select the source of velocity field from the velocity field list. By default, the mobility SI unit is S point molar per kilogram for each species is set to be calculated based on the diffusion coefficients, which is based on SI unit square meter per second, specifying the diffusion section and the temperature using the Nernst-Einstein relation. The mobility settings will only have an impact on the transport by migration of charged species as defined by the charge number ZC dimensionless. Specify negative charge using a minus sign. For the electron neutrality charge conservation model, you need at least one positivity and one negativity charge species ion in the electrolyte. Specify the temperature if you are using mobilities based on the Nernst-Einstein relation in the model input section, the water self-ionization section is available for the water-based with electron neutrality option. The section allows the water self-ionization constant to be set using the built-in option. The constant will be set to account for temperature, giving the pH of the simulation the correct temperature dependence. Note that the electrolyte in this case doesn't refer to the pore electrolyte in porous electrodes, which should be defined by a porous electrode node instead. For porous separators, use the separator instead. Electrolyte theory. Domain equations for tertiary current distribution using the Nernst-Planck equations and electrode neutrality. Now I want to go to porous electrode. The porous electrode node sets up charge balances for the electrode and the pore electrolyte in a porous electrode, and as well as the mass balance for the species in the electrolyte. Note that the node should be used for porous domains that conduct current in both an electrolyte and an electrode phase. For the case of domains that don't contain a pore electrolyte, for instance the gas diffusion layer GDL in a PEMF-FC electrode, use an electrode node instead. Use porous electrode reaction child nodes to define the charge transfer reactions that occur on the interface between the electrolyte and electrode phases within the porous electrode. The porous matrix double layer capacitance subnode is also available. See the electrolyte node for more information about diffusion and migration in electric field. Settings of this node. Corrections factors may be specified in the effective transport parameter correction section to account for the lower effective conductivities of the electrode and electrolyte phases due to the lower volume fractions of each phase and the tortuosity of the porous matrix. The electrode volume fraction is used to calculate the effective electric conductivity of the porous matrix when the correction factor is set to the Brugman or tortuosity. Additionally, it is used to calculating the active specific surface area of the porous matrix when particle based area option is selected in the child node. Now I will go to the dissolving and depositing species. See the porous electrode node of the primary and secondary current distribution interfaces, absorbing and dissolving the species. See the electrode surface node. Now I want to go through the film resistance, see the electrode surface node, porous electrode theory, porous electrode reaction theory, domain equations for tertiary current distribution using the layers flag equations and electron neutrality. I want to go through the first chapter, separator. I use separator node to model electron discharge and mass transport in an electronically isolating porous matrix. Use correction factors to account for the lower diffusion coefficients in the electrolyte and the lower conductivities of the electrode due to the lower volume fractions of each phase and tortuosity of the porous matrix. See also the electrolyte note for more information about the diffusion and migration in electric field settings of this node. Dissolving and depositing species. See the porous electrode node of the primary and secondary current distribution interfaces. Now I want to go to the reactions. Use the reactions node to define non-electrochemical reactions in an electrolyte domain. The node is found from the additional sources submenu. Reacting volume. When specifying reaction rates in the RC2 SI unit is molar per cubic meter point second fields for species in a porous electrode domain. The specified reaction rate expression may either refer to the total volume or the pore electrolyte volume for non-porous domains. The settings of the reacting volume section has no impact. The total volume, the reaction expressions are used as specified multiplied by unity. For pore volume, this results in the specified reaction expression being multiplied by the domain electrolyte volume fraction E epsilon L epsilon equals unity for non-porous domains. Now I'm going to go through the initial values. Use this node to specify the initial values of the concentration, electrolyte potential, and electric potential dependent variables to be used by the solver. For many electrochemical problems that use nonlinear electrode kinetics, such as Butler-Volmer kinetics, providing reasonable initial values can significantly improve solver convergence. A good value for the electric potential SI unit is based on both electrode and porous electrode domains can usually be derived from the boundary conditions. For instance, if a boundary has been grounded or set to a cell potential, use that value as the initial value also in the adjacent domain. For the electrolyte potential SI unit based on both, a good initial value is often the negative of the equilibrium potential of the grounded electrode. For the concentration initial values, at least one positive and one negative charge species should have a non-zero and positive initial values. After considering the electroneutrality condition, the initial value for the ion calculated from the electroneutrality condition cannot be said explicitly. Now I'm gonna go to the ion exchange membrane. Use the ion exchange membrane node to specify a domain with a permanent fixed space charge. The node is typically used for defining perm-selective membranes used for various applications such as dialysis cells or flow batteries. The node models that transport of all species added at the interface top node and adds a fixed space charge to the electroneutrality condition. The fixed space charge specifies the charge ions fixed in the membrane polymer matrix. Use negative space charge for cation selective membranes and positive charge for anion selective membranes respectively. Select the apply donor boundary conditions checkbox to enable donor equilibrium conditions on all interior boundaries between the domain selected by the node and all adjacent domains selected by the interface except electrode nodes. The boundary conditions are applied for all species and the electrolyte potential dependent variable. This option is not available for the Poisson charge conservation model option. The Add Donald Shift to Initial Values checkbox, when enabled, shifts the initial values, concentration, and potential values specified on the initial values node. For the active Selection of the ion exchange membrane node in order to fulfill electron neutrality and compliance with the donor equilibrium. It is assumed that the user-defined initial values represents the values for bulk liquid electrolyte in equilibrium with the membrane. The shifted initial values are then used as initial values to the solver. This option facilitates a model setup since it typically excludes the need to sweep the fixed space charge of the membrane to desire non-zero value using an additional solid step. This option is only available for the electron neutrality or the water-based with electron neutrality charge conservation model options. For the remaining settings of this node, see the electrolyte and separated nodes. Ion exchange membrane boundary. Use the ion exchange membrane boundary node to specify an exterior boundary over which the flux of a charge-carrying species is continuous but the electrolyte potential shifts with a specified value. This condition is typically used in electrochemical cells containing both free electrolytes and ion exchange membranes, for instance, in dialysis or flow battery problems. The node is typically used to couple two separate current distribution interfaces, where one of the interfaces models a free electrolyte domain and the other models the ion exchange membrane domain. Note that using the ion exchange membrane domain node often is a more convenient modeling approach if the transported species in the free electrolyte and ion exchange membrane are the same. The node is applicable to exterior boundaries to electrolyte domains for defining ion exchange membranes. On an interior boundary between two electrolyte domains, use the thin electrolyte layer domain node. The choice of the charge-carrying species concentration species specifies that the current flow over the boundary will be carried by this species, which must have a non-zero charge number. Use the membrane potential setting to set the electrolyte potential on the membrane side of the boundary. Note that if this potential is set to the electrolyte potential of a primary current distribution or secondary current distribution interface, no additional settings are needed in that interface to set up the correct boundary condition. The potential condition may be either donor, which will calculate the potential shift over the boundary based on the membrane charge carrying species concentrations, or can be user defined. I want to go through the thin electrolyte layer. Use this node to specify a thin layer on an interior boundary between two electrolyte domains. The node can be used as an alternative to drawing the actual layer as a domain in the model geometry, which may significantly reduce meshing and solver time, especially in three dimensions model. The layer may either be insulating resistive, supporting electrolytes only, or an ion exchange membrane. For resistive or ion exchange membrane, the potential drop over the membrane is determined either from the surface resistivity or the thickness and conductivity. For ion exchange membrane, the choice of the charge carrying species concentration species specifies that the current flowing over the layer will be carried by this species, which must have a non-zero charge number. The potential condition may be either donor, which calculates the potential shifts over the boundary based on the membrane charge carrying species concentration, or user defined. Now I want to go through the current distribution boundary element interface. The current distribution boundary element interface found under the electrochemistry branch when adding a physics interface solves for the electrolyte potential using Laplace equations. The equations are formulated and solved for by the use of the boundary elements method. The interface is available for two dimensions and three dimensions components. Due to the use of the beam Current source terms in electrolyte and porous electrode cannot be used in this interface. The individual node settings of the current distribution boundary elements are in most cases identical to the corresponding modes in the primary and secondary current distribution interfaces. This chapter will only cover features and settings specific for the current distribution boundary element interface. The current distribution boundary element interface chapter, the first section is settings. The default name for the first physics interface in the model is CDBM, and the domain selection. The interface supports selection of voids when the infinite void is selected by the boundary element. Formulation includes infinity. Use settings of the infinity condition section to the set the boundary condition for the potential at infinity. Note that the default domain selection of the interface is all domains and voids, which includes the infinite void, the domain number of the infinite void, which is 0. Another way to add the infinite void to the selection is to click paste selection and type in 0. Now I'm going to go through the symmetry. Symmetry can be a convenient way to add insulating boundaries of infinite extensions. For instance, to model the surface of the ocean in subsea corrosion protection problem. Use the applicable combo boxes to activate a symmetry plane in 3 dimensions, space dimension, and a symmetry line in 2 dimensions, space dimensions, and specify the location x, y, z of the plane line using the plane deposition line position parameter. Far field approximation. The BEM problem is solved which use far field approximation checkbox enabled and using an iterative solver by default. The far field approximation in combination with an iterative solver may in make many cases lead to significantly lower computational load. Now I'm gonna go through the infinity condition. Use the settings of this section to apply a boundary condition for the electrode potential at infinity. The settings are only active if the infinite void is included in the selection. Now I'm gonna go to the quadrature. To display this section, click the Show More option button and select Advanced Physics options in the Show More option dialog. Select the Thin Gap Handling checkbox to increase the accuracy of the quadrature between almost touching mesh element pairs, that is, pairs that are extremely close with respect to the element size. The value in the threshold distance relative to mesh size controls the distance at which elements are considered as almost touching the false value 0.1. A larger value should provide more accurate results but an increased computational cost. Under integration order, the integration order very close elements thin gap option becomes active, making it possible to set a higher order rule for such elements in 2 dimensions. An additional variable transformation is applied to improve the accuracy even further. The settings under integration order are by default set to automatic. This means that quadrature integration order values will follow the element order selection in the discretization section. Higher element orders automatically generate higher values for the quadrature integration orders. The quadrature integration order settings determine the level of accuracy of the computation of double integrals over the singular integral kernels that need to be evaluated for solving the beam integral equations. For contributions from overlapping mesh elements pair, identical elements, elements sharing common edge, or elements with common vertices, specialized regularization transformations are applied before proceeding with numerical integration. For evaluation of contribution from the non-overlapping mesh element pairs, a standard numerical integration is used. Due to the presence of singularities in the double integrals, higher integration order is needed for closed mesh element pairs than for distant mesh element pairs. The following integration order settings are available when you select manual. Now I will go through the integration order distance elements, integration order for evaluating a standard double integral BAM contributions for uh, from mesh pairs separated by a large distance relative to their size. The next is integration order, closed elements. Integration order for evaluating standard double integral BEM contributions from mesh pairs separated by a short distance relative to their size. The next one is integration order, when closed elements thin gap option becomes active, making it possible to set a higher order rule for such elements when the thin gap handling checkbox has been selected. See above. The next option is integration order element with common vertex integration order for evaluating regularized double integral BEM contributions from mesh pairs with a common vertexes. The next one is integration order elements with some and common edge integration order for evaluating regularized double integral BEM contributions from mesh pairs with a common edge. The next is integration order same element integration order for evaluating regularized double integral BEM contributions from identical mesh pairs. The next one is integration order weak contribution, integration order for evaluating a standard single integral BEM contributions. This integration doesn't contain any singularities. Now I want to go through the current distribution type. The selection from the current distribution type list governs how electrode reactions are modeled on interfaces between electrodes and electrolytes. Models using a proper current distribution type use potential constraints, Dirichlet boundary conditions, according to the equilibrium potential setting. Secondary current distribution models use current flux conditions, Newman boundary conditions according to the sum of electrode reaction current densities. Now I want to go through the physics versus materials preference electrode potential, the physics versus material reference electrode potential setting on the physics interface. Node can be used to combine material library data for current densities and equilibrium potential with an arbitrary reference electrode scale in the physics. The setting affects the electrode potential used for model input into the materials node as well as all equilibrium potential values output from the materials node. Note that the setting will only impact how potentials are interpreted in communication between the physics and materials node. If the from materials option is not in use for equilibrium potentials or electrode kinetics, the setting has no impact. Now I'm gonna go to the discretization. In this section, you can specify the discretization orders of the dependent variable and of auxiliary boundary elements method boundary flux variables. Note the discretization order of auxiliary boundary element method edge flux variables is the same as that of the dependent variable. Now I want to go through the edge features in three dimensions for the current distribution boundary element interface. The edge nodes in the interface contain some extra settings compared to the edge node in the primary and secondary current distribution interfaces. When using the edge node in three dimensions, the interface creates virtual tubes around the edge selections defined by the edge radius based on the meter. It is generally assumed that the edge radius is small in comparison to other geometrical measures of the model, such as the edge length and the distance between different edges in the geometry. This usually also implies that the discrete available electrode volume for the charge transport due to the space occupied by the tubes can be neglected. Enable compensate for tube volume to include the effect of the volume of the tubes on the electrolyte charge transfer. Note that the additional degrees of freedoms are introduced in the model when compensating for the tube volume and that this may result in higher memory usage and longer solver times. Now I want to go through the primary and secondary current distribution interfaces, trade physics features in the current distribution interfaces theory for the current distribution interfaces. The chapter I want to go through is shared physics features in the current distribution interfaces, domain boundary pair edge, and point nodes for the electrochemistry interfaces. This chapter describes various domain, boundary edge, point, and pair nodes that are common to several of the electrochemistry interface. Says the nodes are available from the Physics Ribbon toolbar Windows users, Physics Context menu in Macintosh operating system or Linux users, or right-click to access the context menu. All users, the nodes and features described in this section are available for all electrochemistry branch interfaces unless otherwise indicated. In general, to add a node, go to the physics toolbar. No matter what operating system you are using, subnodes are available by right-clicking the pattern node and selecting it from the attributes menu. I will go through the circuit terminal, current conductor, double layer capacitance, electric ground, electric potential, electric reference potential, current conductor, electrode current density, electrode current source, electrode electrolyte boundary interface, electrode potential, electrode power, electrode reaction, electrode surface, electrolyte current density, current source, and potential, external short, harmonic perturbation, highly conductive porous electrode, initial values for absorbing, dissolving species, initial values for dissolving, depositing species, insulation, internal electrode surface, perforated electrode surface, internal electrode surface, line mass source, load cycle, non-Faradaic reactions, perforated electrode surface, point mass surface, pores electrode reaction, pores matrix double layer capacitance, reference electrode symmetry, thin electrode layer, thin electrode surface. For the tertiary current distribution Nernst-Planck interface, these nodes are available and described for the transport of diluted species interface. In the COMSOL Multiphysics Reference Manual, see Table 2-4 for links to common sections and Table 2-5 to common feature notes. You can also search for information. Press F1 to open the help window or Control plus F1 to open the documentation window. Now I will go through the theory of the current distribution interfaces. Current conductor. Use the current conductor node to define an electrode domain that only conducts current in the electron conducting phase. The node is typically used for modeling solid metal electrodes, current collectors, current feeders, gas diffusion layers, and gas bakings. The electric conductivity sigma S in SI unit is based on the S per meter parameter will define how the current in the domain depends on the gradient of the potential. Electrode theory, a highly conductive porous electrode. The highly conductive porous electrode node defines a charge balance of the pore electrolyte in a porous electrode, and for interfaces solving for electrolyte species, the corresponding mass balance for the species in the electrolyte. Use this node when electric conductivity is high enough to assume uniform potential in the electron conducting phase of the porous electrode. See the electrode surface node for the description of the electrode phase potential condition in harmonic perturbation sections. See the porous electrode node for the description of the remaining settings. Electrode current source. Use the electrode current source node to define contributions to the current density from electron current sources. The current source is QS. SI unit is based on the ampere per cubic meter is added according to the following equations. IS is equal to QS, where IS is equal to minus sigma S delta QS, and QS denotes the electrode's conductivity and Phi the electric potential. To use this feature, click the Show More option button and select Advanced Physics options. In the Show More option dialog, then add the node from the Additional Sources submenu. Now I'm going to go through the electrolyte current source. Use the electrolyte current source node to define contributions to the current density in the electrolyte from, for example, reactions or other effects. The current source QL SI unit is based on ampere per cubic meter is added according to the following equation. To use this feature, click the Show More option button and select Advanced Physics options in the Show More options dialog. Then add the node from the Additional Sources submenu. Now I want to go to the porous electrode reactions. The porous electrode reaction node defines the electrode kinetics for a charge transfer reaction that occurs at the interface between the pore electrolyte and electrode matrix. A porous electrode. The node can be added as subnode to a porous electrode node. Add multiple nodes to the same porous electrode node to model multiple reactions, for instance, in mixed potential problems. See the electrode reaction node for a description of the equilibrium potential, electrode kinetics, stoichiometry coefficients, and heat of reaction section. Now I'm gonna go to active specific surface area. The active specific surface area RV that in SI unit is based on a square meter per cubic meter specifies the area of the electrode electrolyte interface that is catalytically active. For this porous electrode reaction, RV is multiplied by I location defined in the electrode kinetics section to produce a current source in the domain. This section is not available for primary current distribution interfaces, porous electrode reaction theory, electrode kinetics expressions, porous matrix, double layer capacitance. Use the porous matrix a double layer capacitance subnode to define a non-Faradic double layer current density at the interface between the porous electrode matrix and the electrolyte. The resulting double layer current source in the porous electrode domain depends on the time derivative of the potentials and is proportional to both the electrical double layer capacitance CDL SI unit based on Faraday per square meter and the double layer area RVDL SI unit is 1 divided by M. The node can be added as subnode to a porous electrode node. Use this node to simulate transit analysis techniques such as AC impedance analysis and current interrupt studies. Note that for stationary problems, the double layer current is zero. This node is not available for the primary current distribution interface, and for stoichiometric coefficients, use the settings of the stoichiometric coefficient section not available in the primary or secondary current distribution interfaces to control what the species are participating in double layer charging, that is the mass exchange between the double layer and the electrolyte outside the double layer. The number of participating electrons should be chosen so that the mass exchange is scaled correctly to the double layer charging current. The stoichiometric coefficients (VR) should be chosen considering the situation when the porous electrode is being cathodically polarized. In other words, use a negative stoichiometric coefficient for ions species Si that are transported into the double layer of the electrode that is being cathodically polarized. Typically, the cations and positive stoichiometric coefficients for ions species Si that are transported out of the double layer, typically the anions. Insulation. The insulation boundary condition describes the wall of a cell or the boundaries of the cell that don't face a conductor. The boundary condition imposes the following equations: iK multiplied by n is equal to 0, where iK denotes the current density vector and K is equal to L. S is an index for the electrolyte and electrode respectively. And I want to go to the symmetry. For the primary current distribution and secondary current distribution interfaces, symmetry boundary conditions is identical to the insulation condition. For the tertiary current distribution nearest Planck interface, symmetry boundary condition imposes a no flux condition for the molar flux of a species at a boundary. Now I want to go through the symmetry theory. Electrode surface. Use electrode surface node to model an electrochemical electrolyte interface between an electrolyte domain and an boundary, where the electrode is not included explicitly as a domain in the model geometry. Set the electric potential of the electrode or specify a current condition that the potential of the electrode shall fulfill, and use subnodes to specify the electrode reaction and the double layer capacitance at the interface. This node can only be applied on outer boundaries to electrolyte domains. For interior boundaries between electrolyte and electrode domains, use internal electrode surface node. For interior boundaries to electrolyte domains, use the perforated electrode surface node. Now I want to go through the dissolving depositing the species use setting of this section to define species that participate in the solution deposition electrode reactions. For instance, metal deposition, dissolution, or oxide formation. Use the add plus and delete buttons as needed in the table to control the number of species, the density and molar mass in conjunction with the reaction rates and stoichiometry defined in the electrode reaction subnode. Determine the normal electrode growth rate. The growth rate can be used in conjunction with the deforming electrode surface and non-deforming boundary multiphysics couplings to model geometry deformation. Then the solve for species concentrations variable checkbox is selected. Dependent variable for the molar surface concentration of the dissolving depositing species are added. These can be used to model the thickness of the dissolving depositing layer in time-dependent simulation where the resulting deformation in the model geometry is small and will have negligible impact on the current distribution. In stationary studies, the molar surface concentration variables will be defined but not solved for by default. When solving for the species concentration variables, corresponding thickness variables are defined that you, for instance, can use to couple the film resistance. See the blue sections. Now I want to go through the deposition dissolution rates, growth velocities, and thicknesses on electrode surfaces. Species conservation on deforming geometry. In deforming geometry simulations, they compensate for boundary stretching as the tangential convection term based on the movement of the mesh to the mass balance equations of the dissolving depositing species surface concentrations. Absorbing and dissolving species. Use the settings of this section to define species that can absorb and dissolve or an electrode surface during charge transfer or non-Faradic reactions. The density of size parameter will be used to set up the local surface mass balance equations for the triactional surface covers. Use the plus and delete buttons as needed in the table to control the number of species. The name of each absorbing dissolving species can be edited in the first column of the table. Use a site occupancy number larger than unity for species that occupy more than one site at the electrode surface. According to the settings of the table, the fractional surface coverage variable names will be defined according to x66.theta underline z, where 3x is interface name, 3 is the tag of the electrode surface node, and 3z the species name. The variable 3x dot theta free underline 3 they represents the fraction of free surface sites. The variable names can be used when defining kinetics parameters in electrode reaction subnode. Use the surface reaction interface to model surface diffusion. Film resistance. Use a film resistance if you want to include an additional potential drop due to an ohmic resistance at the interface between the electrode and electrolyte, for instance, due to build-up and insulating deposits. Specify either a surface resistance or film SI unit is based on ohm point square meter directly, or choose the thickness and conductivity option to calculate the surface resistivity based on a depositing film thickness. Now I'm going to go to the harmonic perturbation. Use this section in conjunction with XCR impedance studies types to control the perturbation amplitude in the frequency domain. The perturbation parameter is either electric potential, electrode potential, total current, or average current density based on the boundary condition selected in the next section. The frequency spectrum is specified in the study note. Electrode phase of potential condition. This section specifies the potential and the electrode phase of the electrolyte electrode interface. The electrode potential is used via the overpotential by the electrode reaction subnodes. Use the electric potential option to set the value of the potential explicitly with respect to the ground, whereas at the electrode potential will set the potential value with respect to a reference potential. Total current, average current density, external short and load cycle all add an extra global degree of freedom for the potential and electrode phase, set to comply with the chosen condition. When using the total current option in one dimension or two dimensions, the boundary area is based either on the cross-sectional area one dimensions or the outer plane quickness two dimensions properties set on the physics interface top node. In the lithium-ion battery and the battery with the binary electrolyte interfaces, if the defined cell state of the charge SOC and initial charge inventory checkbox has been ticked in the cell settings section on the physics interface top node, the total current can be specified either explicitly or as a multiple of the series current variable. Uh, triple X dot I underline wants to underline cell where triple X is the physics interface tag that is defined by the global SOC state of the charge and initial charge distribution node. The load cycle setting activates a load cycle child node where the settings for this option are located. See also the documentation for the electrode potential and external short nodes for further information about these boundary conditions. Cyclic voltammetry. The cyclic voltammetry setting varies the electric potential linearly in time as follows when used in conjunction with a cyclic voltammetry study step. You see that we have a y-axis electric potential based on the volt and time on x-axis. The figure 3 dash 1 it shows electric potential versus time generated by the cyclic voltammogram boundary conditions. The linear sweep rate is 100 millivolt per second. The number of cycles to potential level are also shown. More advanced waveforms can be obtained using the electric potential option with a parameter setting based on functions found in the definitions menu. Now I'm gonna go through counter electrode analysis only. This boundary condition is only available for the electroanalysis charge conservation model in the tertiary current distribution Nernst-Planck-TCD interface. The control electrode option sets a potential to ensure an overall charge balance of the cell so that the integral of all electrode reaction currents of all electrode surface node evaluates to zero. See also current electrodes and overall charge balance, advanced cyclic voltammetry settings. To display this section, click the Show More option button and select Advanced Physics options. In the Show More option dialog, cyclic voltammetry is selected. As the boundary condition, the checkbox add events as vertex potentials in cyclic voltammetry and smoothing of cyclic voltammetry wave functions are both selected by default. When smoothing of cyclic voltammetry wave functions enabled, smoothing is applied on the triangular wave around the vertex potentials. The smoother factors default to 1.10 to the power of minus 3. The smoothing zone corresponds to the product of the smoothing factor with half the duration of one period of the triangular wave. When add events at vertex potential and cycle photometry is enabled, solver events are added at the vertex potential for the cycle photogram when the vertex potentials are reached. These events cause the solver to stop, reinitialize some variables, and then continue. This typically improves solver convergence in addition by forcing the time-dependent solver to resolve the time steps when the vertex potential are reached. The solution accuracy is improved, especially if the solver is set to the output solutions before and after events. Now, when I go to the equilibrium potential handling primary condition. This settings only has an effect if there are multiple electrode reaction subnodes present and if either a current distribution initialization study step using current distribution tie or the primary current distribution interface is used. The setting determines which equilibrium potential value will be used for defining the primary current distribution constraints. When the first reaction has been selected, the first electrode reaction subnode must be active in the model. To display this section, click the Show More option button and select Advanced Physics options in the Show More option dialog. Now I'm going to go to the constraint settings for the primary current distributions. The use of weak constraints will in some cases give a more accurate value of the local current density during the solver process. This may in turn render more accurate results when coupling to the local current density variable to describe other phenomena in the model. For instance, when modeling geometry deformation due to the electrode dissolution deposition, the section is available in the primary current distribution and secondary current distribution interfaces when the current distribution model property has been set to the primary. This section is only available in the primary current distribution and secondary current distribution interfaces when the current distribution model property has been set to primary. To display this section, click the Show More Options button and select Advanced Physics options in the Show More option dialog. Electrode reactions, theory and film resistance. Now I want to go to the electrode reactions. Electrode reaction subnode defines the electrode kinetics for a charge transfer reaction that occurs on an electrode interface boundary. Use multiple nodes to model multiple reactions, for instance, in mixed potential problems. The parent node can be either an internal electrode surface or an electrode surface. Note that all settings described below are not available for all electrochemistry interfaces. Now I'll go through the electrode reaction story, equilibrium potential. The equilibrium potential EEQ SI unit based on the word is used in the electrokinetics expressions. The electrokinetic section via the definition of the over potential or for the setting of primary current distribution potential constraints. The equilibrium potential can be defined either in the materials node from material by using the Nernst equation or by using the user-defined expression. If the Nernst equation is used, the concentration dependence is calculated automatically based on the reference equilibrium potential EEQ reference volt. For all interfaces except the tertiary current distribution interface, the concentration dependence is based on the user-defined reduced species expression CR unitless and oxidized species expression C0 unitless parameters. CR and CO should be defined so that the quotient between them is 1 for the reference state, for which EQ is equal to EQ and reference. In the tertiary current distribution interface, the concentration dependence of the Nernst equation is based entirely on the settings in the stoichiometric coefficients and the reference concentrations sections. When using Nernst equation, additional options are available in the Butler-Volmer expression type in the electrode kinetic section. Now I want to go through the equilibrium potentials and the Nernst equation. Reference concentrations. This section is only available in the tertiary current distribution interface if the equilibrium potential has been selected to be defined by the Nernst equation. The reference concentrations define the reference state for which EQ is equal to E equation and reference. Electrode kinetics, the settings of this section will be defined. The local current density I location in the SI unit is based on the ampere per square meter at the interface between the electrolyte and the electrode. Note that allocation for all built-in kinetics expressions types will depend on our potential, which in turn depend on the equilibrium potential defined in the previous section. The local current distribution and the local current density expression, allocation expression based on the SI unit ampere per square meter can be defined either in the materials node from materials by using the form from kinetics expression or by using a user-defined expression for all kinetic expressions. The exchange current density I0 SI unit is based on the ampere per square meter is a measure of the kinetic activity. The exchange current density is typically concentration dependent. Thank you so much for watching my tutorial video